Hi everyone, this is a review of Chapter 4, Correlation and Regression. Now some of you may have not, didn't get to this chapter or you skipped it, and that's okay. Don't worry about it. This is not a very complicated subject, and I believe if you go spend the time and go through your discussion to Cricket Chirps from the beginning to the end, that I think it'll make a lot of sense to you in a very short period of time. So this particular presentation is for discussion to Cricket Chirps and Chapter 4 in your textbook. Scatter diagrams and linear correlation. Studies of correlation and regression of two variables usually begin with a graph of paired data values, x and y. We call such a graph a scatter diagram. A scatter diagram is a graph in which data pairs x and y are plotted as individual points on a grid with horizontal axis x and vertical axis y. We call the x the explanatory variable and y is the response variable. By looking at a scatter diagram of data pairs, you can observe whether there seems to be a relationship between the x and y values. Example 1 is a scatter diagram, and this is actually on page 132 in your textbook on example 1. Phosphorus is a chemical used in many household and industrial cleaning compounds. Unfortunately, phosphorus tends to find its way into surface water where it can kill fish, plants, and other wetland creatures. Phosphorus reduction programs are required by law and are monitored by the EPA. There's more information on page 132. So this particular problem is asking us to make a scatter diagram for these data. So here are the data values. There's 1, 2, 3, 4, 5, 6, 7, 8 points. And here are the x values and y values. So notice on here there's 1, 2, 3, 4, 5, 6, 7, 8 data values as above. So when you're graphing these, just as a reminder, x is the horizontal axis, y is the vertical axis. You graph the x and then the y. You walk before you run. These plotted points constitute the scatter diagram. To make the diagram, first scan the data and decide an appropriate scale for each axis. So this is going to go along the painful process of actually creating the scatter plot or scatter diagram. Now we're going to interpret the relationship between the x and y shown in figure 4.1. By inspecting the figure, we see that the smaller values of x are associated with smaller values of y, and larger values of x are associated with larger values of y. So it looks like there's a relationship here. Roughly speaking, the general trend seems to be reasonably well represented by an upward sloping line segment as shown in figure 4.1. Of course, it's possible to draw many curves close to the points in figure 4-1, but a straight line is the simplest and most widely used in elementary studies of paired data. We can draw many lines in figure 4.1, but in some sense the best line should be the one that comes closest to each of the points in the scatter diagram. So they're talking about how they actually constructed the line. When we're using our data analysis software, we do not have to be concerned with the actual computation of the line. We're more interested in what the line represents. If the points of a scatter diagram are located so that no line is realistically a good fit, then we can say the points possess no linear correlation. We see some examples of scatter diagrams for which there is no linear correlation in figure 4.2. So there's no line that goes through all those points, and there's no line that fits these points either. In figure 4-4, we see some diagrams with perfect linear correlation. So this is moderate linear correlation, and this is perfect linear correlation, where all the points are on the line. Figure 4-4 parts B and D show variables that are negatively correlated. So as the values in x increase, the values in y decrease. as the explanatory variable increases, the response variable decreases. If we go back one slide, these have a positive relationship. These have a positive relationship, and these have a negative relationship. Looking at a scatter diagram to see whether a line best describes a relationship between the values of data pairs is useful. In fact, whenever you are looking for a relationship between two variables, making a scatter diagram is a good first step. There's a mathematical measurement that describes the strength of the linear association between the two variables. The measure is called the sample correlation coefficient R. The full name for R is the Pearson product moment correlation coefficient, named in honor of the English statistician Karl Pearson, who's credited with formulating R. And this is how you actually calculate, these are actually properties of R. The sample correlation coefficient is a numerical measurement that assesses the strength of a linear relationship between two variables x and y. R is a unitless measurement between -1 and +1. In symbols, -1 is less than or equal to R, which is less than or equal to 1. If R is 1, there's a perfect positive linear correlation. If R equals -1, there's a perfect negative linear correlation. If R equals 0, there is no linear correlation. The closer R is to 1 or -1, the better a line describes a relationship between the two variables x and y. Positive values of R imply that as x increases, y tends to increase. Negative values of R imply that as x increases, y tends to decrease. The value of R is the same regardless of whether the variable is explanatory, of which variable is the explanatory variable and which is the response variable. In other words, the value of R is the same for the pairs x, y, and the corresponding pairs y, x. The value of R does not change when either variable is converted to different units. So the textbook goes into the development of the formula for R, and I included that here for your reference, but you're not responsible for actually calculating the R value. You can use software for this from now on. If there is a positive linear relationship between the variables x and y, then high values of x are paired with high values of y, and low values of x are paired with low values of y. In the case of negative linear correlation, high values of x are paired with low values of y, and low values of x are paired with high values of y. This relationship is pictured here below, 4-6. If there is little or no linear correlation between x and y, however, then we will find both high and low x values, sometimes paired with high y values and sometimes paired with low y values. This relationship is shown here below. Okay, looks like I need to download that slide. Again, it can be shown mathematically that R is always a number between +1 and -1. So this is example 2, computing R. A test site at the Great Sand Dunes National Monument gave the following information about x and y. Construct a scatter diagram. Do you expect R to be positive? Here's a scatter diagram. Figure 4-7 displays a scatter diagram. From the scatter diagram, it appears that as x values increase, y values also tend to increase. Therefore, R should be positive. Using a calculator to compute R directly gives 0.949 to 3 decimal places after the decimal. So, what does the value of R tell you? Since R is very close to 1, we have an indication of a strong positive linear correlation between wind velocity and drift rate of sand. In other words, we expect that the higher wind speeds tend to mean greater drift rates. Because r is so close to 1, the association between the variables appears to be linear. And that example is on page 138 in your textbook. Because it is quite a task to compute R for even 7 data pairs, the use of columns as in 4.3 is extremely helpful. Like I said, I'm not going to expect you to do any calculations like this. I would rather have you understand what the concept behind the R is. This example has to do with Denali National Park in Alaska. The wolf population is dependent on a large, strong caribou population. In this wild setting, caribou are found in very large herds. The well-being of an entire caribou herd is not threatened by wolves. In fact, it is thought that wolves keep caribou herds strong by helping prevent overpopulation. Can the caribou population be used to predict the size of the wolf population? So let X be a random variable that represents the fall caribou population in hundreds in Denali National Park, and let Y be a random variable that represents the late winter wolf population in the park. A random sample of recent years gave the following information. So remember, X is caribou, Y is wolves. Looking at the scatter diagram in figure 4-9, we can ask some questions. Do the data indicate a linear relationship between X and Y? So if I go back to the slide beforehand, does it look like a line could fit and in between and summarize these data points? Can you find an equation for the best fitting line relating X and Y? Can you use this relationship to predict the size of the wolf population when you know the size of the caribou population? Again, I'm not asking you to calculate the equation of the line, but rather compute it using software. What fractional part of the variability in Y can be associated with the variability in X? Which fractional part of the variability in Y is not associated with the variability in X? The first step in answering those questions is to express the relationship as a mathematical equation. There are many possible equations, but the simplest and most widely used is the linear equation, or the equation of a straight line. Because we'll be using this line to predict the Y values from the X values, we call X the explanatory variable and Y is the response variable. Our job is to find the linear equation that best represents the point of the scatter diagram. So again, the book goes on to explain how to calculate the least squares line. And it gives you the data set and it shows you a solution. So we place the 2 points on the scatter diagram and connect the points with the line segment. So this is actually the line that best represents this data set. If the caribou population decreases by 400, we predict the sustainable wolf population to decrease by 6.4. This summarizes what the slope tells you. The slope of the least squares line tells us how many units the response variable is expected to change for each unit change in the explanatory variable. The number of units change in the response variable for each unit change in the explanatory variable is called the marginal change of the response variable. Some points in the data set have a strong influence on the equation of the least squares line. A point is influential if removing it would substantially change the equation of the least squares line or other calculations associated with linear regression. An influential point often has an X value near the extreme high or low value of the data set. It's similar to an outlier. Figure 4-12 shows the scatter diagram with the influential point removed. Notice that the equations for the least squares line are quite different. So here in this particular slide, the equation is y equals 1.45x plus 1.75, and the other one was 3.47x minus 6.33. If a data